Thank you, Mr. Chairman. And good morning, everybody. I'm Pietro Foti. I'm a postdoc at La Sapienza University of Rome. And today I'm going to present you this work that is about the behavior of notches. As you well know, we can distinguish notches into blunt and sharp notches. And in this particular work, we would like to revisit an old concept that is the concept of a limit notch radius through the average density method. So, what we want to do with this work, as I said, is to show that this method, first of all, is able to capture the entire behavior of notches, so going from blunt notches to sharp notches, and to derive a limit condition that can distinguish this behavior in terms of a notch radius. In order to do so, we carried out some parametric finite element simulation in which we have applied the average density method for a generic material that is uniquely identified by R0, that is a material parameter identified by the method. And after this, we have carried out an experimental validation through literature data with a fatigue dataset of about 700 and more fatigue strength reduction factor data. So work. Okay, first of all, let's talk about the behavior of notches. I think you are all familiar with these two diagrams that are the diagrams of Frost-Miller and the diagram from Kitagawa. Both of these diagrams highlight the presence of a branch point, one for the notches, and one for cracks. I introduced both diagrams, although I'm just talking about only about notches, because in some recent works, recent from 20 years ago, Azzori and Lazzarini demonstrated that these two diagrams can be thought about as a unique diagram in which in which cracks and notches can be thought as two sides of the same medal. And finally, it is possible to obtain a unique diagram like the one on the right in the slide, in which it is possible to consider both the blunt behavior and the sharp notch behavior and defect behavior by introducing a critical value for the stress concentration factor, that is the KT star here. About the method that we considered in this work, it is the average the strain energy density method. That is a method that has been validated to account for fracture both in static condition and in fatigue failure. And the very basic idea of this method is that under static condition, that Berto failure happens when the local strain energy density averaged in a given control volume reaches a critical value. In fatigue is actually the same, but we are talking about a critical value in fatigue condition. The important thing to highlight is that this critical value is independent of the notch opening angle, the loading condition, and the local geometry. I talked about a control volume, and there are several features that describe this particular volume of material that the method to consider in order to average the energy and evaluate the critical condition for a notch. It has a shape that depends on the local geometry. It has a circular sector shape when we are dealing with zero radius notches, and it has a crescent moon-like shape when we are dealing with non-zero radius notches. About the CV position, this is determined following the mode 1 dominance concept, while the control volume characteristic length, so the size of this control volume, depends on the material properties, and it can be thought as a material properties as well. Indeed, as you can see here, we can obtain the value of this F0 starting in static condition from the fracture toughness and the ultimate tensile stress. Under fatigue condition, the method has been applied by making two assumptions. that the failure in physical fatigue happens in linear elastic regime and it shows a brittle nature. By doing this assumption, the cyclic average strain energy density is considered as the parameter to account for fracture. And as you can see, it has been validated during the last 2 decades for considering failures for starting from different failure initiation point, different loading condition, and for different materials. Regarding the limit condition that I was talking about before, we have done some assumption. Our first assumption was that this limit condition can be found only in terms of geometrical terms, and in particular by looking at how the control volume is defined when dealing with notches. In particular, you can see two different conditions here. There is the one on the top that is the one when you have the control volume that ends on the part of the radius, part of the notch that has a curvature, while in other condition, this control volume ends on the notch edges. This condition can be schematized and can be solved in terms analytically, and it is possible to find this value for the radius that we have called here rho sharp. I will explain later why we have call it this rho sharp and not rho limit. We have done some simulation and we have estimated the fatigue strength reduction factor according to the method through this equation here. And by doing all this simulation and plotting the results in terms of ratio between the stress concentration factor and the estimated value of the fatigue strength reduction factor versus the ratio between the sharp radius and the actual radius of considering the simulation, we have obtained for the method this trend here. As you can see, there is a change in the behavior, but the value that we have estimated by making just geometrical consideration is not able to, it doesn't coincide with the conventional branch limit that is usually found in literature. So we have done some fitting in this case, and we have retrieved, sorry, we have retrieved the value for a limit condition in terms of a notch radius. Here you can see the equation that we have estimated through numerical simulation, but although I have not reported it here, it is possible also to derive this analytically. But I didn't have time to present it during this presentation. Once we have done this, we have also summarized all the numerical results, starting from the diagram that I showed you before. So introducing the critical value for the stress concentration factor that was defined by Azzori, Lazzari, and Meneghetti in other terms, but we have evaluated it here by evaluating the stress concentration factor by replacing the geometry that we considered the limit value for the notch radius. So we kept all the geometry the same and we replaced just the notch radius. Obviously, up to now, I've talked just about numerical results, but of course, we needed to have an experimental validation. And we have done this through some literature data. We have compiled a database of more than 700 fatigue strength reduction factor, including iron, various grades of steel, aluminum alloy, titanium, and so on. This is the database that we have been able to achieve. You can see on the left diagram that the value that we have retrieved summarized in terms of stress concentration factor over the fatigue strength versus the inverse of the notch radius. And here the inverse of the fatigue strength reduction factor versus the stress concentration factor. We have considered the first solution that we have presented in terms of limit radius, and you can see here the results of our, let's say, the proposed equation that we have considered. While here you can see the results summarized according to the Azzori-Lazzani-Meneghetti diagram. As you can see, the condition that we have determined in terms of the notch radius appears able to distinguish the blunt notch behavior from the sharp notch behavior. Here you can see all the estimation that we have obtained by introducing this value, this limit value for the notch radius, according to this first equation, this second equation that introduced the limit stress concentration factor, and finally also a summary of our fatigue database according to the conventional average density method. So the conventional way to apply this method. To conclude, we have evaluated with this work the possibility to distinguish blunt and sharp notch in an easy way by by relying on just a geometrical parameter. So practically, when we have a component, we know the material that we are dealing with. By evaluating this parameter, we can have an idea if we have a blunt behavior, so we can proceed by applying a point-based approach to foreseeing the fatigue behavior, or if we need to apply a field-based criterion to foresee the fatigue behavior of a component. Furthermore, introducing this limit condition for the notch radius, it is possible also to establish if we are going to design something and we want to improve its fatigue properties, we can evaluate through this parameter if a change in the notch radius will be effective in improving the fatigue properties. Because if we are in the sharp notch behavior, by changing the notch radius, if we are still in that behavior, we will not see an improvement in the fatigue behavior. With this, I conclude and I thank you for all attention.